So you don't need a bootcamp. You don't need to write Hello World, a counter, a fun game, or anything else like that. You're going to build a real Solana program, also called a smart contract, in the next 30 minutes. You'll be building a swap app, an app that actually handles real value, has an equivalent in traditional finance, and it is the key to understanding how to build anything else on Solana. There's an old saying that once you build a swap app, everything else looks like a swap app. If you're building an auction house, you're going to have to do all the same things this program does. And if you want to build a polymarket style betting app, same thing. Once you know how to build this, you'll be able to build anything else you like. You don't need any prior blockchain experience or Rust experience. We're going to go through the bits of blockchain and Rust you need to make this app. So today, you're going to learn how to make instruction handlers, which are on-chain functions that are part of your program. We're going to learn how to store tokens in your program. We're going to learn how to store custom data inside your program. And we're going to learn how to control access to your program. I want to convince you that this is the best video to learn Solana. So I'll say that I taught this privately for a couple of years, and since then, I've taught it to more than 250,000 people here on YouTube. And this isn't a video where you watch someone type, I promise. Instead, we're going to take a repo where all the tests are already created for us. We're going to go step by step through each individual instruction handler and work with them until the tests for that instruction handler pass. We'll have animated diagrams along the way to show the tokens moving between accounts, and I think it's a really great way to understand how to build an app that you'll be able to use to build anything else. Let's go. So why a swap program? What does it do? A swap program handles a situation where somebody wants to swap some amount of one thing for a different amount of something else. In this case, Alice wants to swap 10 USDC for 100 bonk. And Bob comes along and he likes that offer, so he accepts it. Alice and Bob have swapped. Bob has received Alice's USDC and Alice has received Bob's bonk. But what if Bob is a bad actor? What if Alice sends her USDC to Bob and then Bob just leaves because maybe Bob's just that type of guy? The real challenge here is ensuring that Alice and Bob can swap without having to trust each other. So here's how they handle that in traditional finance. Alice sends her funds to a trusted third party, and that trusted third party will hold her funds in escrow until Bob has done the same. Once both sides have completed their part of the transaction, the trusted third party distributes the funds to their destinations. But, as you can see, also takes a percentage for itself. This is really how most traditional finance works. Whether you're buying a coffee or sending money overseas, someone's taking between 1% and 6% of the transaction, which is a huge amount of money. Blockchain solves this with a swap program. So let's reset for a moment. Alice still has her USDC and she wants to swap it for some bonk, and Bob likes that offer. Rather than using a third-party financial institution, they can use a Solana program. These are called smart contracts on older blockchains. Each side gets 100% of what the other side offered, without a middleman taking a percentage of the transaction. Now, there are transaction fees on Solana, but they are a small fraction of a penny, regardless of the size of the transaction. Let's look inside the program and see how it works. If you don't understand the next part, watch the Understanding Solana Token Accounts video linked in the show notes. So here's Alice. She has a Solana account. And she has 2 token accounts for USDC and for bonk. Alice wants to swap 10 USDC for 100 bonk. So we create a Solana program, which you're going to do today, to handle this. It's going to have 3 instruction handlers. These are on-chain functions that someone can run to perform some action, like moving tokens around on the blockchain. The instruction handlers will be make offer, take offer, and refund offer. You'll be building all of those today. So when Alice makes an offer, she runs the make offer instruction handler. And the first thing it's going to do is save details about the tokens Alice wants in return to a data account. As well as saving details about what Alice wants in return, we'll take the tokens from her USDC account and save them in a token account that's owned by our program, with the authority set to Alice's specific offer. So here's Bob, and Bob also has some USDC, and he has a whole lot of bonk, and he really likes Alice's offer. So Bob will run take offer, specifying the offer account he wants to use, and Bob will take the offer. Now, Alice doesn't need to be awake, online, or anything else throughout this process. She's already done her part, and our program will do the rest. So the first thing our program will do is move the tokens from the Vault account into Bob's USDC account. The next thing it will do is take the tokens from Bob's bonk account and send them directly to Alice. We don't need any intermediary accounts here. We'll close the Vault account because we don't need it anymore and return the rent to Alice. And that's it. Both sides have received 100% of what the other person offered without a middleman taking a percentage of the transaction. It's the same speed as traditional finance, and as we said before, the fees will be a tiny chunk of a cent. So open a terminal and let's build this. So here I am in my terminal, and the first thing I'm going to do before I go any further is set up a nightly version of Rust to use. Right now, Anchor uses the versions of Rust that are produced each day, and to ensure that my build is consistent, I'm going to use a known good version of Rust. So I'm on a Mac, which means I use Z shell by default. So I'm going to modify my ZSHRC. In your case, this might be bashrc, for example, if you're on Linux. So I've got this option here. For consistent Anchor builds, I'm going to set Rust up toolchain to be that particular version. Once that's done, I'll close that and just do a source, whatever my shell config file is, to reload the changes. Now that I'm done, I'm going to clone our starter repo. So we're just going to call it swap program, and we're going to change into it. And then I'm going to run a little degit command. Degit, if you haven't used it before, is just a tool that downloads files from Git. It doesn't keep any of the Git history. It just provides you a direct file download of a particular branch. So npx degit, and then this address below, don't worry, it's in the show notes. We'll pull down our empty project. And then we can now see that all those files are in our directory. If I start my editor, we can see our project. It has a README at the top level, just saying what it does, a license, all the normal things. The biggest thing is that this is an Anchor project, so we have our top-level anchor.toml that describes a bunch of things that are relevant to the entire project, and then multiple Anchor programs inside the programs directory. So we have programs escrow, swap, same thing, and we have another cargo.toml there that defines our dependencies. We've mentioned we're using Anchor, obviously. We've also turned on a feature called init if needed that allows us to create accounts if they don't already exist. And we've also turned on support for Solana tokens, in other words, SPL tokens with the same version of Anchor. Our Anchor program, as I said before, lives in our programs directory, and the place where our program starts is in this librs. That does a couple of imports, particularly this anchor-lang prelude, which is most of the things you see in Anchor. Then it sets up an ID. This is a Rust macro that generates some code to say that this program is deployed at this address. And then we have our actual program, which literally is just a normal Rust module. We create a module called escrow or swap, same thing, and we have multiple functions inside that are part of that module. The thing that makes this a Solana program is this really cool program attribute, which takes that normal Rust module and turns it into a Solana program that we can deploy on the blockchain. It'll add a bunch of features to this code to get instructions off the chain, send them to the right function, etc. Our instruction handlers are inside our handlers directory. We have make offer, refund offer, and take offer, but we haven't filled any of those in this repo. So the first thing we're going to do is create our offer account, which describes the tokens provided by the person making the offer and what they want in return. So if you open up state offer.rs, there's an empty struct there. A struct, by the way, is the Rust equivalent of an interface from TypeScript. It's a bunch of keys and values with the type specified for each key. It's pretty boring watching people type, so I'm going to do a cut and paste, but I'll go through it all now. We begin by importing the Anchor prelude, which gives us access to all the Anchor keywords in this file. And then we create our struct. We've got two little Anchor attributes we've attached here. One is an account, which says this is a Solana account, something we're going to store on the blockchain, and derive init space, which allows Anchor to easily calculate the total amount of storage needed to store this data. So we have our struct, which we call offer, an ID, which is going to uniquely define the offer. ID will actually be provided by the client, but don't worry, we'll do some checks to make sure that they're not trying to reuse an existing offer ID. The maker, which is the address of the person that is making the offer. Token mint A. A is the thing that maker is providing, B is the thing that taker is providing. So we have the token mints for A and B. A token mint is a way of uniquely describing a currency or a particular type of token on Solana. The amount of token B they want in exchange, and finally a bump. Because the address for an offer is actually calculated by particular input seeds, the text offer and an ID, we save the bump because that's used to calculate that address, and this will speed things up a little bit later on. Save that file, and then let's go and create make offer. So now that we've created our offer account type, we can go and create the make offer instruction handler. You'll recall that it does two things. The first is create the actual offer account, which stores details about what the person running make offer wants in return. And the second thing is take the tokens from the person running make offer and store them into a token account owned by our program. We'll call that the vault. The authority for the vault will actually be our offer account. So later on, you'll see when we move tokens from this account, we'll move them as the offer data account that we just made. So let's go build. Let's go and create make offer, our first instruction handler. Again, it's pretty boring watching people type, so I'm going to do a cut and paste, but don't worry, I'll go through every line of code just like before. So we have our imports. We import the Anchor prelude. Again, that gives us access to all the keywords from Anchor. We import offer as well, and our error codes as well, which I've done for you because that's pretty boring. We have a shared module in this project, which is called transfer tokens, and it's just a wrapper function for transferring tokens. And finally, because we're working with tokens, we're going to import a bunch of things from Anchor SPL, which is the SPL token program. It's the program that handles every token apart from Sol. There's a couple of things which are a little bit interesting about this. There's the associated token program, which allows us to find where an individual wallet stores a particular token. And this thing called token interface, which is a wrapper around either the older or newer token programs. It allows us to either handle traditional token program or the newer token extensions program. Now that we've got everything we need, we're actually going to create another struct before we make up the function. The struct is going to define our account constraints. They are rules on the accounts provided by clients. So firstly, people need to provide all these accounts. And secondly, you'll see there's a little bit of extra logic we have to ensure that those accounts match particular criteria we set. So in Solana, when people make transactions, they also provide a list of the accounts that will be involved in that transaction. That allows Solana to process instructions that are working across different accounts at the same time. So we're going to create a struct that describes those accounts and some rules around their use. So we have the pub struct make offer, and to say that this is our account struct, we use #derive accounts. Also, because people running make offer are going to provide the offer ID they want to use, we add this instruction ID attribute that allows us to access the ID in these rules. So the first account people have to provide is the associated token program. You probably know about that already. It allows you to find where a wallet stores a particular type of token. The next thing is the token program. This is using this interface type that allows us to work with both the traditional token program and the newer token extensions program. Next, we have the system program, which is just used to make accounts and do nearly anything on Solana. You'll probably always have the system program included as an account. The next account is the maker, and the type is signer. That means that the account called maker must actually have signed this instruction. We're also going to add the attribute mutable here because the signer is going to pay to make the accounts in this transaction. We have token mint A, which is a mint account, and we're going to have some rules to make sure that token mint A is using the same token program as the actual token program account. Likewise, token mint B, it's another mint, same rules, make sure it's using the same token program. It can use the older token program, it can use the newer token program, it just needs to be consistent. We have maker token account A, which is the tokens that the maker is going to put into the vault. Firstly, because we're going to move those tokens into our vault, we're going to add the word mutable here because we're going to deduct from the balance of this account. We're going to check the mint actually matches token mint A. We're going to check the account is actually owned by Alice or the maker or whoever signed the transaction. We're going to check that the token program is consistent as well. Then we've got this offer account, and we're actually going to make this offer account, which is why we have this init here. The init rules also say if you're trying to make an offer account and that account already exists, it will actually throw an error, and we'll check that in our tests. The person who is the maker or who signed the transaction will also pay to make this offer account. And the space needed is the init space, which is the space for all these things, plus this thing called the discriminator, which is just a little bit of data at the beginning of the account where Anchor saves the account type. The seeds, which is used to make the address for this account, is just the offer and the offer ID. The extra bits of information you see here are just converting that into bytes. And then finally, because this is a PDA, we have a bump that's also used. There's one more account we'll have to make, which is the vault itself. It's just a token account. We're going to say init because we're going to create it. Maker will pay to create it. The mint must be token mint A. The authority will be offer. In other words, the offer data account owns this vault token account. and the token program must be consistent with the token program we've used elsewhere, either the older one or the newer one. So now that we've done our imports and created the account constraints that we need to check when people call this function, let's make the actual function. I'll paste it in again and let's go through it. So the first argument for any Solana instruction handler is always this context. Through that, you can get a whole bunch of information about how that instruction handler was called, things like the program ID, etc. More to the point, the next few arguments, ID, token A offered amount and token B wanted amount, are all provided by the person calling this instruction handler. In other words, they're all provided by the incoming instruction. So Alice, when she wants to make an offer, will specify these three things. I mentioned earlier that Solana instruction handlers just return a result of an empty value. The actual changes are written out to the blockchain. So if you want to see the updated offers after this is made, you go and get all the offers. The first thing we're going to do is just a bunch of validation. We'll check that the offered amount and the wanted amount is more than 0. We'll throw an error if they're not. We'll make sure that the token mints are different because no one wants to swap something for a different amount of the same thing. One of the two people in that transaction are probably being ripped off. The next thing we'll do is transfer the tokens from Alice's token mint A into our vault. So from maker token account A to token account's vault, the amount is the amount that Alice specified. The mint is whatever the mint of token mint A is. The authority is Alice herself. We'll be using the same token program as the one Alice specified to use, and that's all. If there's an error there, we'll throw up an error, but otherwise our tokens are now moved into our vault. The next thing we'll do is save details about what Alice wanted in return. So we're going to go to that offer account and we're going to create an offer struct with an ID of whatever ID Alice specified. Again, we made sure that wasn't already taken as part of our account constraints. Who made this offer? In other words, Alice. The token that Alice is providing, token mint A, the token that Alice wants, token mint B, the amount of token B that Alice wants, and finally we'll save our bump for performance reasons. Once that's done, we've done everything we need to do as part of make offer. We'll just return OK with an empty value and make offer is complete. We'll save that and I'll just make sure that our librs is updated to include all these options. And there we go, librs is now pointing to our make offer file, which is taking all those options, transferring the tokens, and saving the details about what Alice wants in return to that offer account. Brilliant, we can now go run our tests. So here we are back in our terminal. Now the first thing I'm going to do is just install our npm dependencies because I didn't do that earlier. And after that, I'm going to do an anchor test. This is going to build our program, and once it's finished, it's going to run all our tests. So we're finished, and obviously we haven't finished writing the program, so some of the tests have failed, but if you scroll up, you'll see all the tests for make offer have succeeded. So obviously we can successfully create an offer with valid inputs, that's great. But also, I mentioned before when we were making the offer account, that if the offer ID already existed, that would fail, and that's working too. We have a bunch of checks for if the maker has insufficient token balances, if the token mints were the same, if they wanted or were offering 0 tokens via anchors require. Those all work too. And we can get all the offers after we've made them as well, so we can see the offers we've actually put on the chain. Awesome, you've now made your first Solana instruction handler. Guess what? We're going to make takeoffer now. So let's quickly review what takeoffer does. Takeoffer is run by the person who wants what's being offered, in this case Bob, and it's going to do two things. The first is move the tokens from the vault to Bob's token A account, which is where he stores the tokens that match what's being offered. The second thing is move the tokens that Bob is sending in return straight from his token B account to the maker's token B account, in this case Alice's token B account. Alice now has the tokens she wants and Bob now has the tokens that he wants. Let's jump back to our editor and start takeoffer. Just like before, we'll do our imports, and that includes the anchor prelude, anchor SPL to handle tokens other than sol, the offer struct, the errors I set up for you, transfer tokens, and also close tokens account, which is another shared helper. The next thing is to create the struct of account constraints for the accounts people provide when they need to run takeoffer. So just like before, this is a regular struct, but we add the derive accounts to tell Anchor that this is a set of account constraints. We're going to use the associated token program, either the older or the newer token program using token interface, just like we did with makeoffer, and the system program to create accounts. Now we're going to have a new account called taker, which will be whoever signed this transaction. And that will be mutable because they'll be paying to make the accounts in the accompanying function. We'll also need to refer to the maker, so that's included as well. Token mint A and B, just like with makeoffer. Taker token account A, that's the account that's going to receive the tokens from the vault. Now, the taker may not already have the tokens they want, so we're going to put in it if needed there, just so we can make it if we need to. The taker will pay to create that account, and we're just going to check that the mint, authority, and token program are correct on that account. We have the taker's token account B, which we will use to send the tokens straight to the maker's token account B, and we're going to debit that account because this is the account that we're sending tokens from, and we'll also check the mint, authority, and token program just as we did before. And we have the maker's token account B. That's going to receive the tokens the maker asked for. And again, because the maker may not have the tokens that they want in return, we're going to run init if needed there. The taker will pay to create this, and we're going to run a few checks on the mint, authority, and token program. We also have the offer account itself. We're going to find it using the string offer and then the offer ID. And we're going to close this account after this transaction, and we're going to send a little refund to the maker. We'll also do a couple more checks on it. And then finally, we've got the vault, which is where the taker will receive the funds from. That's going to be mutable because we're going to be taking tokens out of the vault, and we'll just do some checks on the mint, authority, and token program for that vault, making sure that the vault is owned by the offer account and the token program is consistently either the older or the newer token program. Great, that's all the account constraints we need for the takeoffer function. Let's go and make the takeoffer function. So here's our takeoffer instruction handler. As always, the first argument is context, and you're probably wondering why takeoffer isn't specifying an offer ID in here. And the answer to that is really simple. The offer ID is actually set as part of the account constraints. So when people run takeoffer, they're going to have to specify an offer account, and that's the offer that will be taken. So as I said before, takeoffer does two things. The first is move the tokens from the vault to their destination. Now, that vault is actually owned by our offer account. So we're going to specify the seeds of the offer account, which are the word offer and the offer ID. We'll convert them to bytes, as well as the bump that the offer account uses. We'll wrap that in another array because sometimes there can be multiple signers. In this case, there's only one. And then we'll just use our transfer tokens helper again, this time specifying from the vault to the taker's token account A, the amount from the vault, the mint, which is token mint A, the authority, and again, our vault is owned by the offer, the token program we're going to use, and the signer seeds, which are just the seeds used for the offer account because that owns our vault. Next thing we're going to do is close the vault. So we have another helper, close token account. It closes the vault. It's going to send the rent back to whoever made the vault in the first place. Finally, we'll transfer the tokens straight from the taker to the maker. And we're just calling transfer tokens again from the taker's token account B to the maker's token account B, just like that diagram you saw earlier. And that's it. You've now finished takeoffer. So let's go run our tests and see if they pass. So here we are back in our terminal, and let's run anchor test. We will rebuild the program. And what we should see here is that all our makeoffer tests pass, and as well, all our takeoffer tests also now pass. That's looking good. So you can now see that makeoffer works as it did before, but now our takeoffer test pass as well. So people can successfully take an offer, and it will fail if they have an insufficient token balance. That's awesome. So let's drive this home and finish off refund offer. So what if Alice has made an offer, and after a little while, nobody takes the offer, and she just wants her money back? Well, we can create an instruction handler called refund offer. And when Alice runs that, it's going to do two things. The first is take the tokens from that vault account and return them to Alice's token A account. The second thing is to close that vault account and return the rent back to Alice. Let's finish this off. So let's implement refund offer. I'm going to paste because you don't want to watch me type, but just like last time, I'll go through every bit of code for you. And as you'll start to recognize now, nearly every file begins with importing the anchor prelude, which gives us access to all the anchor keywords. Because we're dealing with tokens rather than just sol, we'll also import anchor SPL. We'll import the transfer tokens and close token account helpers we used earlier, and the offer we made, and the error codes I made for you. Just like the other two instruction handlers, we have a struct with accounts, their types, and any rules for them. And we put hash derive accounts to tell Anchor that this is that struct. We have our token program, which just like last time, we'll be using interface, so it can be the older token program or the newer token program. We'll be using the system program because you use that to create accounts and close them and everything else. The maker will be the person signing this transaction. We'll be using token mint A because that's the only token used in this transaction, the one that Alice put into the vault. We have our maker token account A, that's where Alice originally stored the tokens she put into the vault. It'll be mutable because we're changing the balance, we're changing the data for that account. And we're just going to check that the mint, authority, and token program on that token account are the same as what we expect. We have the offer account, and we're actually going to close that account and send the rent back to Alice. Because we're closing the account, it's mutable. We're going to check some of the data inside and make sure the seeds conform to offer and then an offer ID. Finally, we have the vault, and we'll just be checking that the mint, authority, and token program for the vault are what we expect. The actual function for refund offer is very similar to take offer. Because the vault is owned by the offer account, we're actually going to sign the transaction using your offer account's seeds. In other words, the word offer and the ID number of the offer. Then we'll just transfer the tokens from the vault back to Alice's account, and then we'll close the token account and return the rent to the maker. And that's it for refund offer. So let's run our test for hopefully the final time. So our make offer tests all still work, our take offer tests work, and now we can see our refund offer test work as well. Congratulations, you've now made a real Solana program that actually handles value. It receives tokens from users, it distributes them out to other users, it controls access to the program, it writes data accounts and manipulates the data inside. Well done. If you like this, subscribe to QuickNode's YouTube channel, and I'll see you in the next video.